So it's a great pleasure to be in Korea again. This is my second time. First time was 15 years ago at a group theory conference. And so I'd like to thank the organizers for the opportunity to come here again. So what I want to talk about is give you a start on the arithmetic invariants of hyperbolic manifolds. So by arithmetic, I mean number theoretic. And we'll be looking always at the situation that Craig Hodgson was looking at in his talk, where we're looking at our manifolds are hyperbolic, so they're H3 modulo a lattice, and they're possibly non-compact, but they're of finite volume. Okay, so complete hyperbolic three manifolds of finite volume. And in fact, it's convenient not to restrict just to manifolds. If we require that gamma here will be a subgroup of the isometry group of H3. And in fact, again, for convenience, I'm going to assume also orientable. There's no big restriction in saying things are orientable because you can always take the orientable double cover. So then gamma is a lattice in the orientation preserving isometries of H3. And this is PSL2C. And if we simply say it's a lattice, in other words, a discrete subgroup so that the quotient has finite volume, it may have torsion, in which case M, instead of being a manifold, is what's called an orbifold. Locally, it looks like the quotient of R3 by a finite group. And it's very convenient not to make a big distinction and to allow orbifolds as well. So this is our basic situation, and we're interested in now in understanding these from an arithmetic point of view. And now then, rigidity, the Mostow-Prasad rigidity implies, as Craig mentioned in his talk, that in fact everything that happens here is in terms of algebraic numbers, so that after conjugation you actually have gamma, instead of sitting inside of PSL2C, you can actually put it in a PSL2 of a subfield of C, which is a number field. In other words, a finite extension of the rational numbers. Okay? And it would be nice to think of this N that you get this way, this field. So in other words, you can write gamma as 2 by 2 matrices, but with coefficients in this number field. It would be nice to think of this number field as a field of definition, as it were, for the manifold. But there's a lot of problems with that. N is not canonical. There's no canonical choice for this number field. So if we're looking for something to play the role of a field of definition, this N is not it. And there are other reasons why it isn't a good thing. So there are many different choices for this N, and I'll come back to what the different choices are later, in fact, what choices are available. So we'd like something better, and the first better object is the so-called trace field. So the trace field I'll denote by capital K. So this capital K, this is a number field which is associated. We can either think of it as being associated with M or with gamma. So we'll write it as K of M, or we'll write it of K of gamma. And what this is the field generated over Q by the traces of elements of gamma. Now, the trace of an element of gamma, PSL2C, this is SL2C, factored by plus or minus the identity. So the trace of an element of gamma is really only determined up to psi. So this is a little bit ambiguous. It doesn't really matter, but let's be precise and let's say in gamma bar, where gamma bar is going to be pi inverse of gamma, where pi is the projection from SL2C to PSL2C. As I said, I would often doesn't bother to be quite so formal about it, because if you've got things defined up to plus or minus 1, the field they generate is of course unchanged.
What's the relation between that and this K?
Between...
You said there's a number field, it's because this is rigid. Gamma sitting in PSL2N.
Gamma is sitting inside, yes, so n, these traces will certainly be in this n, so this is certainly a subfield of this n. But it's a much more canonical object, okay? K is canonically associated with M, while n is not canonically associated with M, okay? There are many choices for n, but there's only this one choice for K. So this is already much better, but it's still not quite what one would like, because for many purposes, when you're looking for at a manifold, you're really only interested in the manifold, at least for many invariants, you're only interested in it up to commensurability. So let me just remind you what that means. We say that M1 is... Pardon?
Excuse me, is K a finite extension?
Yes, K is a finite extension of Q. So this is a number field. Okay. So let me just remind you that when it says that M1 is commensurable with M2, this is simply defined to mean that they exist finite covers so let's say M1 prime mapping to M1, M2 prime mapping to M2, with M1 prime and M2 prime being the same manifold, so being diffeomorphic and therefore isometric by rigidity. Or in terms of the groups gamma, it's saying that up to conjugation, when you can conjugate your gamma 1 and your gamma 2 so that they intersect in a finite index subgroup of both. Okay. And it turns out that the trace field changes if you, or can change if you take a finite cover. So that if you want an invariant that doesn't change under commensurability, the trace field is not the one. Now there is a nice finite index subgroup that turns out to be small enough that its trace field is then invariant. So what we do is we define gamma 2 simply to be the subgroup of gamma generated by squares of elements. Okay. So if you think about it, you've got gamma. If this will be a normal subgroup, and its quotient will be a group where every element has order 2. A group with every element of order 2 is an abelian group, and it's of course finite because every element has order 2 and it's finitely generated. So we have this mapping from gamma to the abelianization of gamma, and then to the abelianization of gamma modulo abelianization twice it. So this is some z mod 2, some power of z mod 2. And the kernel of this is this gamma squared. Okay. So the kernel of this composed map, I should say. The kernel of gamma going to this z mod 2 to the r is this gamma upper 2. And it's a theorem of Alan Reed that if you take the trace field of this, then you do get a commensurability invariant. Only depends on m or gamma up to commensurability. So we call this field k of m, or little k of gamma, using a lowercase k, a small k. Okay? And this is called the invariant trace field. So we have that k of m is actually, it sits inside of k of m. The index is some power of 2 to the r0, where r0 is actually less than or equal to the r you see here. And there's actually a natural homomorphism of this group, this z2 to the r, to the Galois group of this extension. So this is a normal extension with Galois group c2 to the r. So the thing that is invariant under commensurability is in general a subfield of the trace field, but it's not a very, you don't have to go very far below the trace field because the difference is just some Galois extension of order a power of 2. So this turns out to be the right invariant. If you're looking for something that can play the role of a field of definition, as it were, there are many reasons for seeing the invariant trace field as being the right thing. And let me just mention one very beautiful recent thing where it's come up as being the right thing. And something that I won't have time to go into in detail, but there's the so-called volume conjecture, which is one of the, I would say, probably the most important current conjecture about invariance of hyperbolic 3 manifolds. And this conjecture, there's something called the Jones polynomial, which is associated to a knot. So you have a knot in a 3 manifold. You will assume it's a hyperbolic knot in a 3 manifold, and the Jones polynomial is a polynomial associated to that knot. Now then, there's actually varieties of it indexed by a number n, and these are called the colored Jones polynomial. So these are polynomial invariants associated to a knot k. So k in S3 is what's called a hyperbolic knot, as Craig was describing in his lecture, in the previous lecture. The complement of a knot in S3 is usually hyperbolic. It's very rare that the complement of a knot is not hyperbolic. Okay? And the volume conjecture says that if you look at Jn of k, so I said this is a polynomial, so we can apply this polynomial to e to the 2 pi I over n, to a primitive nth root of unity. And the volume conjecture is the conjecture that as n goes to infinity, this is asymptotic to e to the n over 2 pi times the hyperbolic volume of this knot complement. Okay. So this conjecture has been verified for very few knots. It's been verified for the torus knots. It's been verified for the figure 8 knot, the knot that Craig was talking about in the previous lecture. People differ on whether it's been fully verified for the 5-2 knot, but I think I would say it's been verified for the 5-2 knot, but that's about all there is. There's some links for which it's known, but it's been verified in extremely few cases. However, in the cases where it has been verified, in particular for the figure 8 knot, there have been calculations done to work out the more detailed asymptotics of this. It turns out that the asymptotics, if you have this highest order asymptotics, and when you subtract that off, there's some sort of a log term, there's something in n, something times n log n, if I remember rightly, and then a sum of coefficients times n to the minus k. And you get a series in the asymptotics, n equals 0 to infinity, n equals 1 to infinity now, as the additional asymptotics out to infinity. And experimentally, these ANs lie in the invariant trace field. And the conjecture is that they always lie in the invariant trace field, so that the invariant trace field is showing up here in the volume conjecture as the coefficients in this finer asymptotics in the volume conjecture. And in fact, for the figure 8 knot, this is proved. I think that's work of, well, I'm not sure who all is involved. It's Stavros Garofalidis, Donzagier, Gukov, and various people have worked out these asymptotics. And Donzagier in particular, whose interest is number theory, has shown that there are very interesting connections with the series you get here and modular forms. So there's very deep number theory appearing in the volume conjecture, and it's but it's all really open. At the moment, most of it is experimental work. So anyway, this is the invariant I want to talk about, this at least to start. So this invariant trace field is a kind of field of definition for our manifold. So K of M, this is a number field, but it's more than a number field. Notice that we came up with this number field as a subfield of the complex numbers. So it's a number field with an explicit embedding in the complex numbers. And this is what I like to call a concrete number field, as opposed to an abstract number field. Okay. So let me just remind you of a little bit from Professor Choi's lectures about number theory. So the point is, when you have an abstract number field, it has lots of different embeddings in the complex numbers. Let's quickly review how that comes about. So let's suppose K is an abstract number field. So what this means is that K is an extension of Q, and it's a finite extension. Okay? And then you have the theorem of the primitive element, which says that in fact K is generated by a single element. You can always find a single element which generates K over Q. Now then, this alpha, since the dimension here is finite, K over Q is a finite dimensional vector space, we know that the powers of alpha, which will generate K as a vector space, must be linearly dependent, and we take the first powers which are linearly independent, they'll form a basis. and that gives us the minimal polynomial. There'll be some linear combination with q coefficients of powers of alpha that is 0, and that gives us the minimal polynomial. So that'll be a polynomial f of x of some degree, let's say x to the n. We can always make it monic by dividing by the first coefficient. With the property that f of alpha is equal to 0. Okay? And now we can, the way we turn our abstract number field into a concrete number field is by picking a root of this polynomial that actually lies in C. Okay? So, over the complex numbers, our f of x is a product of x minus alpha I equals 1 to n. The polynomial over the complex numbers factors completely. Our number field, of course, it's given, it's a quotient of the polynomial ring by the ideal generated by f of x, and it maps to C simply by taking the class of x in here, which is to any one of the zeros alpha I of this polynomial considered as C. So what we see is exactly n different embeddings of our field into C, and our concrete number field is simply picking one of these embeddings. And as you learned in Professor Choi's lecture, these n embeddings split up. These n embeddings split into, there'll be a certain number of complex conjugate pairs of embeddings, and that number is usually called R2. So R2 complex conjugate pairs of embeddings. And then R1 embeddings where the image is in the real numbers, and they're called real embeddings. And so the total number, which is R1 plus 2R2, has got to be equal to n. Okay? And the number field that comes from, so this invariant trace field, it's very easy to see it has to be a complex embedding. Okay? And therefore, in our case, for us, R2 is greater than or equal to 1, and the given embedding is one of the complex embeddings. Now I'd like to make a point about number fields. Right? If one hasn't done any algebraic number theory, or even if one has actually, if one hasn't come across fields that kind of arise in nature, what one tends to do in algebraic number field and number theory and then elsewhere is one tends to look at Galois extensions because there's no real restriction in looking at Galois extensions. Any field extension is contained in a Galois extension, and Galois extensions are much easier to handle. But the fields that arise in nature, like these invariant trace fields, are very, very rarely Galois. Why would one expect that? So K of M is rarely a Galois extension. Well, let's think about it simply in terms of these embeddings. How do we see the Galois group, the group of automorphisms of K that fix Q? Well, any automorphism of K that fixes Q when composed with an embedding gives a new embedding, but with exactly the same image. And conversely, if you have an embedding with exactly the same image, you can compose the inverse of the one embedding with the inverse of the other to get a Galois automorphism. So the Galois group of K over Q is in bijective correspondence with the set of tau I, such that tau I of K is equal to tau 1 of K. And there's no reason to expect this to be large. After all, let's take a random example. Let's take a cubic polynomial. F of x is equal to x cubed plus a2x squared plus a1x plus a0. Okay? And remember, we're assuming we always here have a complex field. The fields that occur have to be complex fields. So if this is the minimal polynomial for our field, so if f of x is the minimal polynomial for k of m, then it has to have a complex root. Then the root that gives the concrete embedding is not a real number. But what does this mean? If alpha is not a real number, then we have another embedding given by alpha bar. And since complex roots come in complex conjugate pairs, the third zero of this polynomial has to be real. So we have two complex zeros and the real zero. Well, if we look at the real zero and ask what other embeddings have that same image, there is only the one real zero, so only one real embedding. So the Galois group in this case is trivial. Okay? The Galois group is automatically trivial in this case. So if our polynomial happens to be cubic, the Galois group is trivial. And in particular, we see that the embedding that comes from the fact that K of m is a concrete number field is the only embedding with the given image. You can't find another embedding with a given image. And this already has strong consequences. Here's a very quick consequence of the fact that K is not equal to K bar. Okay? So let me say it this way. K is not equal to K bar, where we're thinking now of K as a concrete number field, as being given with its embedding into the complex numbers. On the other hand, it's very easy to see that if you reverse the orientation of a manifold, you replace K by K bar. So we get the theorem that if K is not equal to K bar, then no cover of M has an orientation reversing. Homeomorphism okay. And the point I've just made is that generically K won't be equal to K bar. So we've got a very quick proof that most hyperbolic 3 manifolds don't have covers which admit orientation reversing homeomorphisms. But not only that, we've got a very easy test for the existence of orientation reversing homeomorphisms that will work most of the time to give the answer no. So this is a very quick application to show that even though this invariant, the invariant trace field, is a very simple invariant to define, it's really a quite powerful invariant. It immediately gives some strong geometric consequences. So I'd now like to move on to a slightly stronger invariant, which is the so-called invariant quaternion algebra. So again, we're assuming that we have our gamma, which is the fundamental group of our hyperbolic manifold or orbifold, is a subgroup of PSL 2C. And as I said, we lift this, for convenience, we could lift this to something in SL 2C. Remember, PSL 2C is simply SL 2C modulo plus or minus the identity. So every element of gamma lifts to two elements in gamma bar, just plus or minus a given matrix. So SL2C sits inside of the 2 by 2 matrices over C. Okay. And I'll denote by Q gamma bar. This is simply going to be the ring generated by Q linear combinations of, actually I don't have to say generated by, I could simply say it is the ring of, because the set of Q linear combinations of elements of gamma bar is a ring. So this sits inside of M2 of C. So this is some sort of a ring. It contains Q. And we have the following theorem, which is that Q gamma bar is a 4-dimensional algebra over the trace field of gamma, capital K of gamma, and it's a central simple algebra, and as you learned in Professor Choi's lectures, what that means is it's a quaternion algebra. So the center of it, the elements that commute with every element of this algebra, is exactly this subfield, and it has dimension 4 over this. Okay. So it may seem a little mysterious. We're taking Q linear combinations, and somehow magically we've gotten this field, the trace field, in there. But that's rather easy. Notice that if you take the trace of an element times the identity, that's how we embed K gamma. Okay, the trace of an element times the identity is simply the element plus its inverse. So using Q linear combinations, you automatically get all traces in there. So the fact that it's an algebra over K gamma is very easy, but the fact that it's a 4-dimensional algebra needs a little bit more work, but is also not too hard. And to see that it's a quaternion algebra is then fairly easy. Now again, we have the problem that because this is an algebra over the trace field, which is not a commensurability invariant, it's not really what we want. So the invariant quaternion algebra which we denote by A of gamma or A of M, depending whether we're thinking of the group or the manifold M equal to H3 over G. This is defined to be Q of this subgroup of index of power of 2, the one generated by squares, lifted. Okay. So this is our second invariant. And this is now a somewhat sharper invariant. So I'd like to describe how much sharper, how much stronger this invariant is than the invariant trace field. So by the way, this of course now is a quaternion algebra over the invariant trace field. So to get a good picture of how much stronger it is, it's a good idea, again, I need to remind you of some material from Professor Choi's lecture. We want to understand the classification of these quaternion algebras. And for that we need a little bit of algebraic number theory, so I'll go back to Professor Choi's lecture and remind you of the fact that that whenever we have a number field, so given a number field K, we have, I'll denote by O sub K, the ring of integers. Remember that a number is an algebraic integer, means that it is a zero of a monic polynomial where the coefficients are all in Z. And this is a very concrete thing. It's a very stable definition. If you're taking an extension field of a given field, you could also say it just has to have coefficients in the integers of the smaller field, and you get the same answer. So it works nicely recursively. So we have OK, the ring of integers of K, and then if you want to look at, and if you look at the ordinary integers are a nice unique factorization domain, with the primes being the irreducible elements that you factor in. But when you go to a number field, unique factorization in general breaks down, and what we know is that you replace unique factorization by factorization of ideals. And as Professor Choi described, you then get the prime ideals. These are the objects that every ideal factors uniquely as a product of prime ideals. And they are the things that replace unique factorization. And yeah, maybe I'll come back to actually doing a little bit of calculation here. If one's a geometer or a topologist and has never had a course in algebraic number theory, this looks more mysterious than it need to. And this is extremely concrete, these prime ideals. It's very easy to calculate everything. And if there's time, I'll show you a little sample calculation. But anyway, you have these prime ideals that are the basis for unique factorization. But as she described, to each prime ideal, you have a distance function given by a norm on K. So you have a norm, the p-adic norm on K, which basically you say a number is small if it's divisible by a large power of the prime ideal. And this gives you a distance function on K. And then you take the usual topological completion of K with respect to this metric. So the completion is the field Kp that she talked about. And this is an example of what's called a local field. A local field is simply a non-discrete topological field non-discrete topological field, and I need another condition. I'm forgetting. Oh, the completeness, of course. I got it by completing with respect to a metric, so it should be complete. Its metric should be complete. Okay? It's a non-discrete, complete topological field. That's the definition of a local field. And these completions that you get by completing at a prime are examples of local fields. There are exactly two other local fields when you're looking at fields of characteristic 0. We're only interested in characteristic 0. So there are exactly two others. And these local fields are the very familiar R and C. They're clearly complete topological fields. Okay. So what we see coming out of the number theory is that we have now some additional embeddings. We have the original R1 embeddings of our field into R. We had the R2 embeddings of our field into C up to conjugation. But if we look at embeddings of K into local fields, we have the completions, K into a completion where P is a prime ideal. And then we have the embeddings K into R. There are R1 of these. And then we have the embeddings K into C. And there are R2 of these. Okay. We think of only R2 of them because they come in complex conjugate pairs. And the complex numbers, we have a convention of putting I up there and minus I down there. But really, that's only convention, so you can think of the two complex conjugate ones as just being related by convention. They differ only by convention of where you put your I. So these embeddings are traditionally called places. Okay? Places is supposed to give the idea of something geometric. The background here, the word place suggests something geometric, and the background is really, you're thinking of K and its ring of integers as a geometric object. Okay. The underlying, you're imagining some kind of quasi-space or other where OK is the ring of functions on this space. And its field of fractions, which is K, is therefore like the field of rational functions or meromorphic functions, the things that you get as quotients of genuine functions. Okay? So OK, well, let me say K is the field of some sort of rational functions on some sort of geometric object, some sort of space. And then the kind of points of this space correspond to the prime ideals and the complex embeddings. And the localizations, the embedding of K into a complete local field, is simply taking the kind of germ of a point. You're focusing in on the point infinitely far and looking at the point really up close and seeing what functions you have there. So that's kind of the geometric background, which is a very powerful idea, and it's in part analogy, in part can be made precise, but it's very powerful in number theory, and it's the reason also that when you look at the prime factorization of primes in a number field that Professor Choi described in her lecture, you have this concept of ramified primes and unramified primes. And this comes from the fact that a field extension from this point of view is the analog of a covering space, but of a branched covering space, a ramified covering space. And the primes being points in this space, you can have ramification at a prime. And when you look at this covering space, ramification refers to the number theoretic analog of what we know as a branched covering or ramified covering in topology. So it's a very useful and powerful analog, but it goes really beyond analog, and it really has powerful uses. But anyway, we have these embeddings into a local field, and we think of it really geometrically as these places as being places in some sort of a geometry, and therefore we talk about a property holding at a place by meaning that if we look at our object and change the coefficients of the object to the coefficients that come from the embedding, the property should hold there. So let me go back to quaternion algebras now. So if A is a quaternion algebra, over a field K, A at an embedding, let me denote these generically by K hat. The completions, I'll always use K hat to mean one of the completions. So K hat is either a KP or R or C, okay? So A at a completion or place K hat means that we simply take A, which of course we saw as a set of matrices, as it were, and what we do is we change, or we saw it as generated by certain generators, we extend our coefficients to the coefficients of K hat. Okay? So this is now a quaternion algebra over the completion. And one of the powerful things is that in many situations you have this local to global principle, which says that if you know things locally, if you know things at every place, then you know it globally. So one has the theorem, A is determined by what it is at the various places. So you know it globally if you know it locally. So i.e., you look at all of the set of A tensor K hat, where K hat runs through all of these different embeddings into a local field. Okay? So this theorem tells us we should understand what a quaternion algebra over a local field is. What are the quaternion algebras over these k sub p's, these R or C? Clearly, with this theorem, that tells us how to classify quaternion algebras. So we have classification of quaternion algebras over local fields. So let me start with C because it's the easiest. The only quaternion algebra in this case is the algebra of 2 by 2 matrices. Okay? For R, we know two quaternion algebras, the 2 by 2 matrices, and then there's Hamilton quaternions, which I'll denote by simply a plain H. The Hamilton's, whoops, capital H, Hamilton's quaternions. Generated by elements I, j, k, all of them square roots of -1, with the property that I times j is k, j times k is I, and so on. And they anti-commute the I, j, k. And then for each kp, it turns out there are, again, exactly these two possibilities. There's always, of course, the 2 by 2 matrices. That's always a quaternion algebra from the point of view of our definition. But then there's also an analog of Hamilton's quaternions. I'll call that H of kp. Okay? And the way it differs from M2 is that these are division algebras. The things in this column are division algebras. Well, of course, 2 by 2 matrices don't form a division ring. You have zero divisors. It's very easy to find two non-zero matrices whose product is 0. So these are not division algebras. These have divisors of 0. Okay. So these are kind of the generic objects. And these are called unramified. And these, the ones that are division algebras, are called ramified. And let me now continue this theorem over here. Okay. So we have the following properties. Let me denote by ram of A. This is going to be the set of embeddings, either complex or real, or into one of these k sub p's, the set of embeddings such that at this place, so the set of places such that at this place, this is ramified. Okay. And we have the following properties. First of all, this is a finite set. And it has an even number of elements. Okay.
You mean the different prime, they are the same?
Pardon?
I mean, this set is finite, mean for different primes, they give the same Hamiltonian quaternion.
No, these will all, this is an algebra over k sub p. So out of the algebra, by looking at its center, you recover what the field is. What I'm saying is that this is a finite set, so finitely often you land in this right-hand side of having a division algebra. For infinitely many of the places, you simply get the matrix algebra over the corresponding local field. But of course, the local fields are different for different primes. Okay? And the second thing is that every such set occurs. In other words, the classification of quaternion algebras is exactly simply the set of finite subsets of the set of places of your field. The set of finite subsets of even size of places of your field. Let's see. I've spoken for an hour and I'm on page 2 of 6 pages, so maybe I should. Okay. So if you want, at this point, you can really forget about quaternion algebras. Really, the extra information given by the invariant quaternion algebra is simply a collection of real embeddings. The only places where you can be ramified for a complex embedding is if that complex embedding is actually real, and a collection of primes, prime ideals. Okay. So that's the extra information that comes from this. And how much extra information is this? So given M, how much better, as it were, is A of M than K of M? Okay. So the first theorem is bad news. If M is non-compact, then A of M is completely unramified, totally unramified. It is just the matrix algebra. It's not giving you any extra information at all. And the proof of this is very easy. Let me say it without writing it down. If M is non-compact, then it has cusps. Remember, what it means for M to be non-compact, here is our M, is that somewhere it's going off to infinity, but as Craig Hodgson described, where it goes off to infinity, it's going off to infinity kind of in a spike, a so-called cusp, with a torus cross-section. Okay. And what one finds is that the elements in the fundamental group of this cusp, they're given by parabolic elements in the fundamental group. So if gamma is contained in pi 1 of the cusp, then gamma as a matrix is conjugate to a matrix of the form 1, 1, 0, and something up here. Okay? Where this means, this tilde means conjugate. Let me write it this way. Gn. Gn. SL2C. Okay. So if it's non-compact, you have parabolic elements like this. But then it's a little exercise to see that gamma minus I is a divisor of 0. Okay? And so in other words, you can't be getting a division algebra. So you must be in this unramified situation. So this looks like bad news. But in fact, it's not such bad news. Let me look at one of the very simplest examples. I'm going to take the example of k equal to q square root of minus 1. And then we'll take the program snap and we look at the data And part of what comes with SNAP and SNAPPy is a database of manifolds. There's the so-called cusp census that comes with SNAP and SNAPPy, which is all hyperbolic, non-compact manifolds that can be triangulated with 7 simplices or less. And then there's a closed census, which looks at small volume hyperbolic manifolds that you can get by doing Dane surgery on elements in the cusp census. And in the closed census, there are 37 manifolds with K of M equal to this particular field. Okay? Exactly 2 of them have A of M equal to the 2 by 2 matrix algebra. So all of the others, 35 of them are ramified. So in 35 cases of these 37 manifolds, the quaternion algebra is giving extra information.